can everyone see my screen? Yeah, okay. Oh, yeah. Sorry. Start the event. Right. Okay. I guess that's everyone. Right, okay, well, let's start. So, proof by induction. So, today we'll cover classic proof by induction and course of values, or strong induction, as some people call it. So, first of all, what is proof by induction? Proof by induction is a way of formalizing a proof so that it holds for all values without having to manually test them. Because that would take forever. And so in a proof by induction, we form our proofs in two steps. A base case where we prove the lowest acceptable value, because sometimes you might have like bounds on n. It's like n is greater than 2 or something. But the smallest value that you can, you'll like manually prove that like by hand. And the second step is the inductive step, where you assume it holds for n equals k, and then prove it holds for k plus 1. And because you've proved that it holds for the next value when the previous one does, it forms like a kind of like domino effect, if that makes sense. Like the next one falls because the previous one does. Does that make sense to everyone? Okay, right. So I have this question. Does anyone want to try it? Or like, do you want me to give you a few minutes? Does anyone want to come up on stage at all? Does anyone have any questions, in fact? Because I kind of sped through that. Okay, right, okay, cool. So we have this sum, and we're told to prove by induction that this is the same as this, where n is greater than or equal to 1, and n is in the natural numbers. So, like I said, our first step is the basis step. So, because n has to be greater than or equal to 1 and in the natural numbers, we'll substitute n equals 1. And so when n equals 1, this means the sum from 1 to 1. So it's just 1, substitute in 1, and you get that 0 equals 0, which is true. So it holds for n equals 1. And then you assume it holds for this. This is just the same, but with all of the n substituted for k. So when n equals k. This next slide looks a bit like, where did you get all this from? But what I've done here is I've just substituted in k plus 1 from the previous sum here and added it on, because that would be the kth plus 1 term. And then I've added it to the other side too, because you have to do on both sides of the equal sign. Okay, now this seems a bit roundabout, but I promise it will make sense. The next step is to simplify, so I just collected it all into k plus 1 on the left side for the sum. And on the right side, I just expanded these brackets. K plus 1 minus 1 is k. K plus 1 plus 1 is k plus 2. Then we factor out 1 over 6k. And I know that seems a bit like random, like a random value. But if you look at our original sum, it has a 1 over 6k in front. So we're trying, what we're trying to do here is match this new sum to the original. Okay, so we pull out the 1 over 6k and then expand everything here into a quadratic, factorize it, and then it looks a bit difficult to see here, but if you can see here, this is really just Okay, I'm sorry. I'm getting a bit lost. Okay, right. So when you factor out the quadratic, you get this. And so this is really just a k plus 1 substituted in disguise. If you look on the next slide, I've overlined it just so you can see it, but this is really just k plus 1 substituted. I'm sorry, this is a mistake. That shouldn't be there. Sorry. So because we've come across this from our assumption that it holds when n equals k, and we've come across it like completely separately, we can say that it holds when it's k plus 1. Does anyone have any questions? Is the stream lag? Oh, my bad. I'm sorry. Let me like restart the screen share. Oh, sorry. What was the last thing you guys heard? What? Okay, all the way from back there. Okay, cool. Okay, so you take out a factor of 1 over 6k, and the reason we do that is because we're trying to match our original sum, the original sum here, because this has 1 over 6k in the front. So, right, okay, take out the factor of 1 over 6k, and then expand everything in this bracket. And I know it kind of seems like where is this going, but once you expand everything, you'll get a quadratic, factorize the quadratic, and it will turn into this, which is really just the same sum, but with k plus 1 in there. It doesn't really look like it, but so k is the same as k plus 1 minus 1, and 2k plus 7 is the same as 2 times k plus 1 plus 5. And k plus 1 is just k plus 1. So if you rearrange it to make everything easier to see, don't pay attention to this. I accidentally put in the same term 2 times. This is really just k plus 1 substituted in. And because we've come across those separately from our assumption that it holds when n equals k, we can say that it holds for n equals k plus 1. Does anybody have any questions before we move on to course of values? Okay, I hear no objections. Either that or my stream's lagging. Okay, cool. Yeah, okay. So course of values or strong induction is quite similar to regular induction, but instead of assuming one base case, like you can use multiple, and the steps are relatively similar. So you prove like manually multiple base cases, you can. And the inductive step, instead of just assuming k, you like assume a whole range of values, all the way from your first base case all the way up until k. So instead of dominoes, I want you to think of this more like a staircase. Like, here we go. Okay, so p of 0 is proved manually. And if p of 0 is true, then p of 1 must be true. And if p of 0 and p of 1 are true, then p of 2 is true. And so on and so forth for all of the values. Okay, do you want me to go through this? Or does anybody have any questions? I'm sorry, Kev. It might be breaking up. My Wi-Fi at home is very terrible. Let me like restart the stream. It becomes like quite obvious how many base cases you need in like while you're doing the question. You might get like stuck at a certain point and realize, oh, okay, I need to prove another base case. You won't need multiple base cases for all of the course of values induction. Only some, like for example, this one, you only really need one base case, but you have to assume the whole range of values holds. Is the stream better, or can everybody hear what I'm saying and see what I'm streaming? Yeah, okay. And does anyone want to do this question? In fact, this is ripped right from one of the tutorials. Does anyone want to try this, or should I just go through it like I did the other one? Yeah. When you say can we go through, like you guys go through alone, or do you want me to like go through what I have on the slides? This is recorded, yeah. Oh, okay, yeah. So the example question, show that for all values of n greater than 1, where n is in the natural numbers, that n is either prime or a product of primes. So it either is itself prime or multiple prime numbers times together. So let's call the property of being prime or a product of primes, let's call that property P. And first, we prove a base case, like any old regular induction. And since n has to be greater than 1, we have to pick 2. And there isn't really much to say because 2 is already prime. There's nothing more to prove, it's just 2's prime, so it is either prime or a product of primes. And then we form our inductive step. So we have to assume that for an arbitrary value of k, all of the values for 2 to k, they hold. So p of 2, p of 3, p of all the way up until k, all of those hold, and begin proving k plus 1. So from here, for k plus 1, there's 2 possible cases. So in case 1, k plus 1 is itself prime, and like we don't really have to prove anything for case 1. It just is prime. There's nothing more to say. And case 2, if k plus 1 is not prime, we have to prove that it's a product of primes. How we do that is because, so any whole integer number is either composite or prime. So if k plus 1 is in case 2, that means it must be a composite number, which means it can be written in the form of a times b. Remember the dot is times. A times b, where a is greater than 1 and b is greater than 1. And the reason they're greater than 1 is because, like, if a was 1, then what would b have to be to get back to k plus 1? It would have to be k plus 1, which would just be like the definition of being prime. It's like either divided by 1 or itself. So because it's in case 2, a and b both have to be greater than 1. And so since a and b times together to make k plus 1, a must be less than k plus 1, and so must also b be less than k plus 1, because they multiply together to make k plus 1. And this is all like occurring in the natural numbers. And since they're less than k plus 1, they have to be, a and b both have to be somewhere in this range of values we assumed hold, which means that p of a holds and p of b holds, which means that they're like either prime or products of primes. And so I'm sure you can see where this goes. Multiplying them together means that k plus 1 holds, because if p of a holds and p of b holds, and you're multiplying a and b, then k plus 1 must also hold, which ends off our proof pretty much. Any questions? Is there anything that didn't make sense? I assume actually like the stream is probably messing up. Really? Okay, cool. Back to the last slide. Yeah. There you go.